Just think about a city for a second. You know, the chaotic ballet of traffic, all those streams of people, that constant buzz of activity. It all seems so random, right? So unpredictable. But what if I told you that underneath all that chaos, cities actually follow a set of hidden, almost universal laws?
I mean, on the surface, it sure looks that way. A city feels like this ultimate complex system, this sprawling organism with millions of independent parts all moving at once. It's messy, it's loud, and trying to predict any of it seems, well, impossible.
But this is where it gets really fascinating. Scientists are discovering that cities, a lot like stars or even crystals, show these astonishingly regular patterns. And by using the tools of statistical physics, we can start to decode the hidden logic that actually governs how cities grow, how they function, and how they evolve. Let's start with one of the most surprising patterns of all.
Okay, so the first big clue to this hidden order is something you probably wouldn't expect: the population of cities. You'd think city sizes would be all over the map, but it turns out they follow a surprisingly strict mathematical rule.
It's called Zipf's law. Basically, what it says is if you rank all the cities in a country from the biggest to the smallest, their populations follow this really predictable decline. The second biggest city will have about half the people of the first one, the third will have about a third, and so on down the line. And the wild part is, this pattern holds up across different countries and even different time periods. It's just remarkably robust.
It's an incredibly simple and, honestly, beautiful pattern hiding in plain sight. But why does it happen? Yeah, the answer isn't quite as simple as you might think.
So why does this pattern emerge? Well, the early models figured, okay, cities just grow randomly, right? Kind of like bacteria in a petri dish. But that theory just didn't match the data. The missing ingredient, it turns out, was migration. A much better model combines that random internal growth with the constant flow of people moving between cities. It's this dynamic interplay, this push and pull, that creates the predictable pattern we see in Zipf's law.
All right, let's go from the size of cities to their internal shape. If we kind of zoom in from the national level to the neighborhood level, we find another really powerful pattern at play, one that helps explain the phenomenon of segregation.
This is explained by something called the Schelling model, and it shows something pretty remarkable. You don't actually need deep-seated prejudice to create a segregated city. All you need is for people to have even a mild preference to not be in the minority right in their immediate neighborhood. This tiny individual rule can cascade into a large-scale, fully segregated pattern. It's kind of mind-blowing.
This slide illustrates the difference perfectly. The image on the left, that's what happens when you optimize for the collective good. You get a nicely mixed city. But the image on the right, that's what happens when each individual just tries to improve their own situation. Even with only mild preferences, you see the city self-organize into a highly segregated state.
You know, this just flies in the face of that classic invisible hand idea that if everyone acts in their own self-interest, it leads to the best outcome for the whole group. In this case, individual choices, even perfectly reasonable ones, can lead to a collective state that's actually far from optimal for society.
So we've looked at the size of cities and the shape of their neighborhoods. Now let's talk about the movement within them. Every single day, millions of people flow through a city in this complex dance of commuting and travel. And it turns out, physics can help us model this too. So the classic approach is called the gravity model, which literally treats cities like planets. The number of trips between two places depends on their populations, their mass, and the distance between them. But a newer and frankly more powerful idea is the radiation model. Instead of some abstract gravity, it models actual human behavior. It assumes a person will travel until they find the first suitable job opportunity. This behavioral approach has proven to be stunningly accurate at predicting real-world commuting patterns, and it often doesn't need all the complicated tweaks the gravity model does.
This brings us to one of the most powerful ideas in this whole new science of cities: urban scaling. The idea here is that as cities get bigger, they don't just become larger versions of small towns. Nope, they change in very specific, predictable ways.
The whole idea is captured in this simple formula right here. You can relate almost any property of a city, we'll call it Y, to its population P, with a scaling exponent we call beta. And the value of that little exponent, beta, tells you a profound story about what's really going on.
There are basically three flavors. If beta is greater than 1, it's called superlinear. Things like patents, innovation, even GDP, they grow faster than the population. This is the engine of innovation. Now, if beta is less than 1, it's sublinear. This represents economies of scale. You need less road surface or fewer gas stations per person in a big city. And if beta is exactly 1, well, it's linear. These are things tied to individual needs, like how much water people use.
But here's a big dose of reality. As powerful as these laws are, they can be kind of fragile. These heat maps, for example, they show the scaling exponent for how many patents get created. The key takeaway? The result changes dramatically depending on how you define the city's boundaries. You know, how much of the surrounding suburbs you decide to include. The so-called law can flip from superlinear innovation to sublinear decline, all based on where you draw the line. In short, the map really matters.
So where does all this leave us? This new science of cities gives us some incredible tools for sure, but it also shows us just how complex the biggest challenges are. Let's take one of the most pressing ones, climate change.
When we try to apply this science to a problem like CO2 emissions, the picture gets, well, muddy. This plot maps the carbon footprint of major world cities against their population. And yeah, while there's a general upward trend, the data points are scattered all over the place. There's a huge amount of variation, and the relationship is nowhere near as clean as something like Zipf's law.
So, are big cities greener? The answer is a pretty frustrating "it depends." Some studies find they're more efficient per person. Others, especially when you start to factor in things like traffic congestion, find they're actually less efficient. And just like with the patents, how you draw the city's boundary can completely flip the conclusion.
And that really brings us to the main takeaway of this whole explainer. The statistical physics of cities isn't some magic crystal ball. It doesn't have all the answers. But what it does give us is a powerful new language and a really rigorous toolkit to understand our urban world, to identify the key forces at play, and to start asking the right kinds of questions.
It leaves us with a final provocative thought. If we could truly understand these hidden laws of scale, of movement, of interaction, how could we use them not just to predict the future of our cities, but to actively design a better one? What would that city even look like?